Hi and Assalamualaikum. My name is Muhammad Akiloman, and I am one of the members for this group for this course MEM360 aka workshop. So for the title for this presentation is Critical Analysis of Casting and Welding Defects and Process Optimizing and Engineering Perspective. So first of all, for the introduction to manufacturing process is a practical lab way overview what we did before the mid semester, which is casting and welding. For casting, we execute both sand casting, which is CO2 molding and green sand cast, CO2 molding and green sand casting workflow. And for the welding, we apply a shield metal arc welding and gas metal arc welding, or we can call it SMAL and GMAL. And for the objective for this presentation is we are going to critically evaluate the defects formation and a strategy how to avoid it from happening. And so for the casting defect, we have about three. And first one is rough surface, as you can see on the red circular red color. And it happened for both of the process. Green sand on the left one on the cube shape, and for the right side, it's a hook shape made by a CO2 molding casting. So both of them somehow have the rough surface defects. And the second one is a shrinkage cavity, which only happen on a green sand casting. As you can see on the black arrow that I put it, there's a bit hollow in it, and there's a shrinkage cavity, or we can call it a hot spot. And for the lastly, it's a flash, some extra metal coming out of the original shape. So that's one of the defects, and as you can see on the blue circular, it's in there. Both of them somehow have the same defects. So for the casting formation mechanism, first of all, for the rough surface, usually rough surface happen because of both of the casting process we're doing using sand as a mold cavity. When you're using sand, the surface is kind of rough, so the product will get a rough surface, the rough finishing. So, and it can also be excessively high pouring temperature and low mold compaction. So when you're ramming the sand, you are not ramming it, you're probably ramming it too fast or ramming it too slow, it can cause a rough surface. So for the second one, shrinkage cavity, or we can call it a hot spot. There's like a hollow in it. So the metal when the finished product, and then you take a look, and there's a hollow in it, like a hole. So this happen because of when you are in the phase of solidification, like from the liquid to the solid, the outer part of the molten metal is going to freeze first. Then after that, the inner part. So when this happen, they're going to pull the metal away from the center. If there isn't any extra liquid metal available, it's going to shrink. It's going to leave a void, a hole in it. So that's why it causes like a blowhole, or we can call it blowhole. Yeah, and it can also be the reason is insufficient riser feed pass and slow heat dissipation take joint cross section. So when you don't have a riser feed, so you have so we can call it you don't have any available extra molten metal, so you will not fully fully the product with a molten metal. So and last but not least, flash fins. And flash fin happen for both of the process, CO2 molding and uh, CO2 molding and the green sand. So we can call flash fin is an extra tin that are being forced to pull out of the original shape. So this happen is kind of different for the green sand and the CO2 molding. So for the green sand, it probably happened because the liquid metal is forced out under metallostatic pressure. So for the CO2 mold, there's a glue while before you clamping both top and bottom of the mold cavity. So when the when you didn't apply the glue, so it will like it will it will force out of the original shape that being designed, and it's also insufficient mold clamping force and dynamic metallostatic head spike or wound tooling joint. If using a not quality joint or not a quality how you clamp it, there's a clamping for the mold cavities. So if the tool is not work very professionally, so it will the flash and fail will happen. It will ruin the product.
Okay, now we are moving to welding defects, which is slat inclusion, porosity, underfill, and excessive spatter. Moving on to the welding information mechanism, let's look at the first two defects. First, porosity occurs when gases become trapped in the weld pool during solidification. This happens when the high temperature arc vaporizes surface contaminants like rust, oil, or moisture into gas. If the shielding gas is disrupted or the whirlpool freezes too quickly, these gases fail into escape. The second one is the inclusion. It happens when non-metallic flux or slag get trapped inside the wet metal, typically driven by poor interpass cleaning, low welding current, or an incorrect electrode angle. Next, we have underfill, which is caused by an imbalance between travel speed and filler metal deposition. Um, when the travel speed is too fast or torch manipulation is inconsistent, the electrode fails to deposit enough filler metal, leaving a sunken valley along the fusion line. And lastly, excessive spatter involves the violent expulsion of molten droplets away from the arc. This is primarily caused by setting the welding current too high, um, maintaining an excessively long arc length, which destabilizes the arc plasma. Okay, for the next one, we are focusing on to environmental, material, and operational root cause. So to summarize the root cause, they fall into three categories: material handling, such as damp electrodes or inadequate preheating; process settings, which is involving unstable currents and erratic travel speeds; and the last one is environmental condition, like high humidity or wind drafts that disrupt the shielding gas. Next, for inspection and quality evaluation methods, we use two approaches. First, visual inspection. Its application is for the initial macro examination of surface profiles to detect immediate visual defects such as irregular bit profiles, excessive spatter, and surface line. Second, liquid penetration testing. Its application is utilization of capillary action penetrance to expose deep, tightly closed surface discontinuities, specifically surface porosity and fine holes that are invisible to the naked eye. Moving on to the inspection and quality process, the first method is visual inspection. So to perform this, we place the casting product on a work table and ensure there is an adequate ambient lighting. Also, we can use a torchlight as an option if the area is dark or shadow. Next, we remove any sand mold residues, slag or flash and burrs from the product surface using a wire brush or chipping hammer. Finally, we examine the surface thoroughly with naked eye to detect any defects. Okay. The second method is liquid penetration testing. So for the first step, we clean the weld build thoroughly by applying spray wine, which is cleaner, and wiping it until dry with a lint-free cloth to remove grease, slag dust, or moisture. Next, apply spray 2, penetrate evenly and allow a dwell time of 10 to 15 minutes for it to seep into cracks or porosity. After that, then paint a clean cloth with spray wine and wipe away the excess red dye. Do not spray the cleaner directly onto the weld to avoid washing the dye out. Finally, apply a thin even a coat of spray 3, which is developer, and allow it to develop for 10 minutes.
Hello, my name is Nasran Hakim Benoni Sams, and my numeric ID is 2024204136. Now, let's compare two different ways to make the molds, which is traditional sand casting and the CO2 mold process. This process both have pros and cons depending what project we make. So the first one is for the sand casting, it is highly flexible and very cheap, especially for simple shapes, since we do not need to have expensive tools to make it. However, it is highly labor intensive, which is requiring a lot of hands-on work and long drying times. This usually leave a rough surface, finish and lower precision on our final parts. And for CO2 modes evolution is this method use CO2 gas to chemically harden the molds almost instantly. It is completely skipping those long manual drying times. It also offers superior precision because the molds holds in its shape perfectly. Even under high heats, the main case is that it is carries a higher cost and requires specialized tools and gas equipment. So, in short, choose sand casting if you want a budget friendly, but if you need a fast result and high precision, choose CO2 molding because it is definitely worth for extra cost. Now we look at process optimization and mitigation strategies. First, advanced digital process control. We use digital sensor to track temperature while pouring the hot molten metal. This will stop trapped air bubbles or gas blowholes from ruining our parts. Second, for manual welding, we add steady physical guides and fixtures. This will support the workers' hands. So every weld is neat, steady, and strong. And for the last one, we use automatic software to log data in real times. This will track our electrical current, voltage change, and cooling cycle instantly to keep everything running perfectly. Now we move to targeted operator competency training. For the first one, we design hand-on practice session so our workers know exactly how to handle raw material before we start building anything. For the second one is moisture control. We train our team to keep a very close eye on the moisture in our grain sand mix. We stop natural error from happening. For the last one is welding techniques and closing. We run specialized training to help our welders keep a steady speed and use the right gun angles. This is the key to preventing slack, inclusion, and cracking. Now, for the last one is specialized equipment and mode optimization. First, we have gas purging lines. So we connect this dedicated gas purging lines directly into our setups. This will clear away any dirty air before the weld solidifies. This will keeping our welding clean and strong. For the second is moisture resistant core binders. We use high quality moisture resistant core binders. This will prevent gas from building up inside the modes and completely eliminates internal core porosity or tiny air pocket. And finally, is gating system and closing. We redesign our gating system and risers to make sure the hot molten metals flow smoothly. This simple change will stop shrinkage cavities from forming as the metal cools and shrinks. Next, let's discuss a very important aspect, which is sustainability, focus, and SDG elements. Let's start with the first column, which is SDG 12, responsible consumption and production. First, we reduce scrap waste by fully reclaiming and recycling our foundry sands in closed system, meaning we reuse the same sand instead of dumping it. For the second one, during manual metal welding, we closely monitor our filler metals and to stop leftover scraps and consumable waste from piling up. And the last is we practice sustainable workshop management by tracking all our raw material carefully so we never buy or consume more than we actually need. Now let's move on to second column, which is SDG 9, industry, innovation, and infrastructure. First, we optimize our machine settings and process variables. This will help us to reduce a massive amounts of electrical energy during heavy workshop tasks. And second is we focus on making high quality, long-lasting weld joints. Because this joint lasts a long time, we reduce the demands to remake or replace parts later on. And lastly, we use modern process optimization to upgrade standard laboratory infrastructure. This turning all these setups into smarter, more efficient workspace. So for the last column, which is technical justifications, by preventing casting and welding defects, we actually stop structural metal waste right at the source, meaning that we do not produce rejected parts. Because we are not remelting and reworking failed parts, we avoid energy intensive process, which directly lower our carbon emission over time. Ultimately, building stronger parts enhance their overall life cycles. This reduce the constant demand for structural replacement and maintenance.
In conclusion, this project proves that understanding defect mechanism bridges theory and practical manufacturing. By identifying defect drivers and implementing systematic NDT, we can optimize production quality. Moving forward, combining digital process control with operator training minimize engineering errors and advance sustainable manufacturing by reducing scrap energy consumption in line with SDG 9 and SDG 12. And that is all from us. Thank you. Assalamualaikum.